Epidemics to Misinformation.
Okay. So I'm one of the organizers, Christian Borgs, of this workshop or of this program on graph limits and processes on networks. The other ones are Jennifer Chase, who was also here, Nicole Imorlika, who is at Microsoft Research, and Amin Saberi, who is at Stanford. And this is a program which is probably might be even more diverse than our previous one. We have mathematicians studying graph limits. We have statisticians estimating these networks. We have epidemiologists. We have economists. And there's some overlap with the other programs. So some of the fellows sort of come to the reading groups for both of them. And so let me tell you a little what it's about, because some of you might not know what a graph limit is. So what is a graph limit? So a graph limit you can think of either an object describing very large graphs or as an object which generates very large graphs. Okay, and one way to do that is you have some function of two features. And how could that? Well, you might be able to guess. Can somebody guess who doesn't know it, how you would use a function of two features? Let me tell you that the function goes into 0, 1. So how I could use a function of two features who generate a LinkedIn graph? So either you know the features because you're LinkedIn and you know sort of the private life of everybody, or maybe some of these features are hidden. So you have some intelligence, you're male, you're female, you have certain degrees, you have maybe you have some hidden qualities like how attractive your writings are. And depending on these features, two nodes will just connect proportional to this function. So this function just describes how attractive two features are to each other. And then you just, if you know nothing, you choose IID random features and then build your network on top of it. And you make it sparse by scaling this with some number, because if LinkedIn has 10 to the 8 members, there are probably not 10 to the 16 edges in that graph. So you make it sparse. Okay. And how would you think of this object as a graph limit? There's a whole theory and we had the first workshop, half of it was mass, which I will not go into, but intuitively, it's very simple. So you take your large network on n nodes. This is your student graph. So these are my students, and these are their PhD thesis. And the first student reads his own thesis. The second gets told he has to read the thesis of the previous student. And the poor last student has to read all the other theses. So that's a half graph. And now I put this graph on a checkerboard. So I just put a white square whenever I is connected to j. So 1 is connected to whatever, 20 here, and so on. And then a limit, you take just the limit of the picture. Okay. So if you take the limit and you squeeze your eyes, well, in this example, it just gives a function which is 1 here and 0 here. But in general, if you squeeze your eye, it will not look that order, so you get a gray picture. And that gray picture is your limit. So in this way, you have for each coordinate x and y, you get the limiting pixel density, and that is this function. Okay. And so, and you can go back and forth between them. So this is graph limits. Now, epidemics, probably most of you have seen these pictures, which I took from Wikipedia. Well, this is not from Wikipedia because of Wikipedia, I was not sure whether I'm allowed to copy it. So that one was one I'm allowed to copy. And you have seen that, okay? But we all know that epidemics actually happens on networks. And this is what this program is. So part of the program is about. So instead of having these differential equations, you have your network of people, and everybody is in some state. Maybe one of them starts infected, everybody else is susceptible. And then you randomly infect neighbors, you randomly recover. And eventually, when the time is over at time infinity, everybody is recovered or dead, depending on the disease. And so that is how you model it on a network. And that leads to all kinds of questions we are addressing in this program, right? Different groups will have different contact rates. Individuals may be more or less susceptible, depending on age, let's say. Highly connected nodes tend to infect more and tend to get infected more. So you have this complicated problem on networks, and there are many interesting questions which we are looking at. How do you want to model the underlying network? You take sort of talk to your mathematicians, they come up with all kinds of networks which all look like trees, and that's not our social networks. You want to predict R0 either from your model, or you want to measure the disease and predict what is R0. And you may want to look at the effect of vaccination or social distancing. So, and finally, what other things spread over networks? Well, we are interested here in economics and spread of information on networks. So a simple example would be, I advertise a new iPhone. I give sort of certain nodes on my networks the information about that iPhone. And then randomly, they tell their friends that they like the new iPhone or not. That's very similar to epidemics. But maybe this is not quite how things work. Maybe it's sort of, you have to convince me of something. So maybe if 50% of my friends say something, I adopt it, otherwise I don't. So that would be threshold models, which are slightly different from epidemics. And there are many related questions. So one of them I may come back to if I have a minute, which is you have some true state of the world. Okay, so Google will either the next time they announce earnings say we made much more than last year, or they will say we made much less than last year. And except for the few Google employees here in the room, we all don't really know that. But there is a truth. Okay, maybe this is tomorrow, so they will either announce this or that. And now you have agents on a network who get some signal about that, perturbed. And now the question is, if they talk to each other, can they learn the true state of the world by combining their signals? And how do you do that? Do that in rounds? Do you do that as a Bayesian who optimizes information? There are many ways how you can do that. And finally, somewhat related is the segregation models, where we have, again, a network, people are neighbors or not. And I'm happy if at most 30%, if at least 30% in my neighborhood look like me, then I'm very happy I'm in a diverse neighborhood. But if I'm just the only one, I feel slightly uncomfortable, I move somewhere else. So, so then the question is, will you get global segregation or not? It depends on the network, depends on the starting conditions. So this is the kind of things we study here with communities which spread very widely. How much time do I have? 30 seconds. Okay. So let me give you some idea of what we do, let me do the next one. No, let me do this one. Okay, so we have these reading groups, very broad, and we have one of the readings group we discussed, what is R naught? Okay, so you may have heard of R naught. It's sort of the expected number of people who get infected from the first individual ever infected in the population. And it's supposed to be a number which is smaller than 1 or larger than 1, determines the epidemic. We all have seen that. But it turns out that this is actually a very complicated thing. Namely, if you have a network with hubs, it really depends whom you choose. If the first individual is a hub, they will infect a lot of people. And that doesn't mean that if this is larger than 1, that doesn't mean the epidemic will take off. If you take a random person, well, you don't have the hubs, that's not good either. So how do you deal with that? Turns out this question we can answer. But if you have short loops, things, again, sort of are really not true. You might think, well, if R naught is bigger than 1, then in the next round, I grow exponential. But if I have loops, then I try to infect the same people in the next round. And so even though R naught is larger than 1, defined like that, you still don't get an epidemic. And so maybe you should say in your network, households have a small short cycle, but maybe otherwise globally it looks tree-like. So maybe we should define R naught for households. And it turns out that you can do that, and you can define, you get an R naught for households and you get an R naught for individuals. They're 2 different numbers. But in at least simple models, they give the same threshold. So it turns out that, and our epidemic friends, we thought of this as a math question, but then, and the statisticians really wanted to know that because they said, well, how do we predict R naught? And then our epidemics people said, well, it's really not clear. It's an abstraction which probably in reality is, its usefulness is very unclear. So it may be sort of some nice picture that you draw curves, and if they're exponential, you say you fit R naught to the rate at which it goes, and if they're going down, and that at least would have this property. But whether that has something to do with how many people you actually infect is very unclear. So this is one of the discussions we had in one of the reading groups with mathematicians, statisticians, epidemiologists. This one didn't involve economics. That would have been the other tidbit I would give you. Good.
Right, and our last speaker for this session is Avishay, also of UC Berkeley. And he's going to tell us about a program coming up this summer here at the Simons Institute on analysis and TCS, New Frontiers.
All right. All right. Hi. Thanks for the invitation to present the program. So this is a program, and these are the other organizers of the program, a wonderful group of researchers that I'm happy to be part of. So let's start with the program logo, this beautiful logo drawn by Barry Buluker. Hopefully by the end of the talk, you'll understand what's in this picture. Yeah, this is a program for summer 2023 about Boolean functions analysis and its connection to theoretical computer science. So analysis of Boolean functions is a powerful toolkit that have been pivotal in the discovery of deep results in countless areas of theoretical computer science and mathematics. And here's like a long list, but it's not actually of all the applications. And you can see also applications in combinatorics, graph theory, social choice, as well as other areas in theoretical computer science. And some of these results are really pretty recent, and they are groundbreaking results, very impressive work. I want to mention that our aim in the program is to extend this toolkit and also to extend the the applications, okay, to apply it in other areas. But the connection between the toolkit and the application is not necessarily one way. Right? It's clear that once we have tools, we can apply them. But oftentimes we see that the applications themselves pose new interesting questions and conjecture about Boolean functions that turns out to be fundamental questions that we didn't know before the application, and they are interesting in their own right. One example comes from the area of artists of approximation that introduced this idea of invariance principle connecting between analysis over the Boolean domain, the discrete object, and analysis over the Gaussian domain. So let me tell you briefly what is the analysis of Boolean functions. So a key concept is the Fourier expansion of a Boolean function. We think of a Boolean function as some function taking maybe n input bits and outputting 1 bit. And we like to denote bits with plus minus 1 for convenience. And a very simple but very useful fact is that every such Boolean function, every discrete object like that, has a unique multilinear representation as a polynomial. So you can write this function as a polynomial. You have one monomial for each subset of the coordinates and a coefficient f hat of s. This is just a real number. This is called the Fourier coefficient of the set S. And it turns out that this coefficient captured very interesting properties of the function that can be used, and in particular that behave nicely with respect to noise operators and with respect to restrictions. Let me give you one example. So let's take a very simple function, the end function. So the end function of two bits, recall that I'm denoting -1 as true or +1 as false. I claim that this function equals this polynomial. And you can check my claim. Just go over all possible 4 inputs and check that the value of the function equals the value of the polynomial. I did this check on the slide. Okay, so what did we get by that? The nice thing that we got is that we express this discrete object as some kind of polynomial over the reals, and this is now a continuous object. So in particular, if we think of the function as defining coloring for these 4 vertices, where red means +1 and blue means -1, now this Fourier representation gives us a continuous function. So now it extends to the entire continuous domain, in this case R2, and we can ask what's the value of this multilinear extension on the point 0.4, 0.5. Okay, it's not a Boolean point, but we still get some answer that has some meaningful interpretation. Okay, so this is just a taste of what is analysis of Boolean functions. Recently, we identify a few trends in Boolean function analysis. So the first trend is go beyond the Boolean cube, beyond the hypercube. So this talks about functions that are not defined necessarily over ±1 to the n, but are defined over certain graphs or on high dimensional expanders. And these have been pivotal in a few breakthroughs, recent breakthroughs. For example, this 2-to-2 conjecture used heavily analysis of functions over the Grassmann graph. You can think of it as some partial result towards the unique games conjecture, which is a big open conjecture in theoretical computer science that would explain a lot of artists of approximation phenomena. And another very exciting developments we have with these high dimensional expanders, using them these recent breakthroughs constructed locally testable codes and also quantum LDPC codes. Okay, so this is the first trend. The second trend is looking inside the cube. This is a little bit like what we saw in the last slide, that the multilinear extension naturally extend the Boolean function to R to the n. So you can also think what's happening inside the cube. And once you do that, you can apply an arsenal of analytical tools on continuous objects. And you can think what happens over the Gaussian space. And you can apply tools from stochastic calculus. For example, here you can see that we're interested in this cube that has all these corners that are colored in blue and red. But we can analyze the behavior on the corners as some kind of continuous walk, maybe a Brownian motion, that sort of changes color as we are getting closer to the corners. Okay, so it turns out that this allows us to to take a lot of ideas from stochastic calculus and apply them to the analysis of these discrete objects. And finally, we have these landmark results about the capset problem, sensitivity conjecture, the Kankal-Lai conjecture, and the sunflower lemma. So now a lot of them are just theorems and not conjectures. And maybe a common theme to all these structural results is that they sort of show that functions that have a specific structure in one aspect, in one measure, also have a nice structure in a different measure. For example, sensitivity conjecture shows that functions that are smooth locally, meaning that the value of the function is similar on every point and its neighbors. They also are simple globally. They can be represented by low-degree polynomials or by shallow decision trees. Okay, so these are the recent trends that we will highlight them in the workshop. We have one workshop for the first topics and one workshop for this topic. And we also listed some motivating questions that we haven't solved yet and we would like to make progress on in this program. We hope that the critical mass of researchers in this area would help us make the necessary advancement on these important questions. So one of them is indeed this unique games conjecture that I mentioned earlier. We already seen the importance of Fourier analysis in the 2-to-2 conjecture. We'd also like to extend Fourier analysis from Boolean functions to high-dimensional expanders, and some work has been done in this direction. Certain barriers in circular bonds might be surpassed if we will be able to analyze the Fourier spectrum of these circuit classes. For example, this constant depth circuit with parity gates, and we have some specific conjectures that we believe are true. And also, with respect to de-randomization and pseudo-randomness, a hot topic in recent years has been to show that you can take any algorithm that has small space and it's randomized, and you can remove the randomness from it without changing space by much. We don't know this yet, but we have several milestones. We achieved several milestones toward that, and we hope that putting researchers on this topic would make us make the next move. And some of these techniques here are Fourier analytic, and some come from, surprisingly, from Laplacian solvers, which is kind of interesting. And finally, we listed some structural conjectures that are still open. Many of them arise from the application, like applications in communication, complexity, learning theory, or quantum computing. And maybe mention just this last one. This Aronson unbalanced conjecture sort of says that on a typical input, quantum decision trees can be simulated by randomized decision trees. And it has so the question sort of boils down to a very particular question about low-degree polynomials, these objects that I showed you earlier. And it has a very interesting new application just this year to this breakthrough result by Yamakawa and Jandry that showed that if this conjecture is true, they are able to get certified randomness from quantum experiments, from single quantum device. Okay, so I'm done. Thanks.
All right, so I guess we can ask questions during the break. We have a longer break right now, half an hour, so we'll reconvene here at 3:10. So I encourage you to ask the program organizers more about their programs, and at 3:10 we'll hear about from Natasha Crooks, also from UC Berkeley, about the Algo Around ACE program. So.
Okay, I think it's 2:45 to 15, right?
Did I get this wrong?
I think Natasha is between 2:45 and 3:15 because we have 3:15 to 5:45 for the.